Good morning, everyone. So our topic for today, so we are still in engineering sciences and allied subjects. Okay, so first topic that we will be discussing will be on engineering mechanics. So engineering mechanics is divided into three parts. So we have the statics. So this will be the topic now, so that we will be focusing today. And the second and third part of engineering mechanics will be focused on dynamics. So a separate recorded lecture for dynamics will be also uploaded. Okay, so I'll be your lecturer. So I'm Engineer Roy Anthony T. Bayon. So we will start. No, so we will start the discussion by presenting some definitions. Okay, or the flow of the discussion would be presenting some theoretical concept or concepts, followed by sample problems. So we will be solving the sample problems for each of the subtopics under engineering mechanics, particularly the statics part for this recorded lecture. So we have here, in the screen, so some of the terms that needs to be defined before we start solving some problems under engineering mechanics, particularly the statics part. Okay, so we have here the definition of mechanics. Okay, and we also have the definition for engineering mechanics. Okay, so it deals with the application of the mechanics to the problems commonly met in the field of engineering practice. And for the statics part, okay, so from the word statics, so meaning to say we can relate it so to a body at rest. Okay, so meaning to say the topics that we will be discussing today or under this recorded lecture will be involving bodies at rest with uh, forces subjected on it. Okay, and then we have the definition of force. So the interaction between two bodies that produce deformation and or affects the motion of bodies. So basically, if you can remember in your high school days, or perhaps in the early engineering days, so force is basically defined. So it's defined as a push and pull. Okay, if you can remember that. But we can further define the definition of the force as the interaction between two bodies that produce deformation and or affects the motion of bodies. And then we have the components, so components of the force. So depending on what dimension we are referring to, for two-dimensional system, so we have the x component and the y component of the force. Okay, for three-dimensional system, so of course we have the x, y, and z component so of the force. So we use the concept of trigonometry. Okay, so we use the concept of trigonometry to identify also the components of the force on each of the axis. No? So we have, for this example, so we have a force, no? So a force acting, no? So at a certain angle with respect to the x-axis. Okay. So the x component of the force is given by the mathematical formula, of course. So that's F cosine of theta, and of course the y component. No, so that's the magnitude, no, of the force multiplied by sine of theta. So for this topic, no, so components of a force, so we will be discussing two. Let me check. No, so we have two sample problems. Okay, so to illustrate, no, how we use, no, so the concept of components of a force, no. Okay, so, and then later on we apply this concept, no, so to the succeeding topics. So it is best, no, so that we fully understood, no, so how we can calculate, no, how we can calculate the components of a force with respect to a particular axis. Okay, so we have here in example number 1. Okay, so in example number 1, so we have a force P. Okay, so a force P, so of 235 Newton. So N stands for Newton. So that is acting at an angle of 60 degrees, no? So with the horizontal, okay, so a force P, or a force of 235 Newton, no? So acts at angle of 60 degrees, no, with the horizontal. So actually it's pulling up a block resting on a 22-degree inclined plane. So basically we have the block, okay, so which is situated, no, so in a 22-degree inclined plane. Okay, so determine the component of P along the plane. Okay, so one of the method, no, on how we approach worded problems like this is to draw the what we so called free body diagram, or FBD. Okay, so we will try to solve, no, so this problem. So get the data first, no, of the example number 1. Okay, and then we will be solving it in a while. Okay, so 235 Newton force acting at an angle of 60 degrees with the horizontal. Okay, so to take note, no, so it is acting at an angle of 60 degrees, no, so with the horizontal. So pulling up a block, okay, so resting on a 22-degree inclined plane. Okay, so we are asked to calculate, no, so the component of P along the plane. Okay. So basically, in our problem, so we are presented with, no, so assuming this would be the horizontal, okay, and then you have there the inclined plane, this one. So as per with the problem, no, so the inclined plane, so this would be the reference, no? And then that would be 22 degrees. So we have there the block. Okay. So this would be the block. Of course, this is the inclined plane. Okay, so it is resting, no? So the plane is inclined, no? So 22 degrees, no? So with the horizontal. And according to the problem, a force P, no? So is acting, okay? So a force P is acting 60 degrees, no? With respect to the horizontal. So, meaning to say that there is a force P, so which is being used to pull the block, okay? So this would be the horizontal, not the horizontal force, but the force P, so which is 235 Newton. Okay. So with reference to the horizontal, so with reference to the horizontal, so the force 235 Newton acts at an angle of 60 degrees. Okay. So if you try to take a look at this one, okay, so the force P, okay, so is, or the force, no, so 235 Newton is acting 60 degrees, no, with respect to the horizontal, not with respect to the block. I mean the inclined plane, no. So we are being asked to calculate, no, so according to the problem, what is the component of the force that is, or what is the component of the force along, no, so the inclined plane. So if you try to look at, so we are being asked this component. So we label this one as, let us say, force F. So this would be the force component. So being asked, no? So in the problem. So if you try to take a look at this one, so the component, no, of the force along the inclined plane with respect to the horizontal will have an angle of 60, no, not 60, but it's 22 degrees. Okay. So horizontal, so this would be another imaginary reference line with respect to the reference, no? So the force P, 235 Newton, so that's 60 degrees, no, with respect to the horizontal. And then the component of the force, no, so labeled with F, no, so that is acting 22 degrees, no, so with the horizontal. So thereby we can calculate, no, so we can calculate the angle between the two forces. So this would be 60 degrees minus 22. So this would be, upon calculating it, we have there, okay, so that would be 38 degrees. Okay. Now, if you try to take a look at this one, okay, so we will be redrawing, no? So this force and might as well this force, no? So that would be force F, and then another, so this would be 235 Newton. So this would be force F. So to allow or to make the analysis easier, so we can set, no? So we can set this one as our x-axis, and this one will also be our y-axis, no? And then this would be, the angle between the two is 38 degrees. Okay. Now, if we try to calculate, no, so the component F, then we can say that F is basically 235 cosine of 38. Okay? So that is equivalent to So make sure that your calculators, your calculator is set to degree mode, so such that the uh, component force F, so is equivalent to 185.2 Newton. So this would be the component of the force along the plane. Okay, so let us check, if we have the answer, from the choices given in the problem. So there you go, so the answer, so to the problem is 185.8 Newton. So this is the component of the force P along the plane. Okay. So but when asked the component of the force along the or with respect to the horizontal, so that would be another story. So you have to calculate the horizontal force P. But since the problem is asking for the component of the force, so along the inclined plane, so the answer would be 185.8, 185, So upon calculation, we have calculated 185.2 from the choices. So the closest is 185 Newton. Okay. So we'll go to the second example. Okay. So again, so since we are showing screens alternately, so you are advised to take note, So take note of the um, you have to take note, of the data presented, in each of the support problem. Okay. So for example number 2, so we have here a 100 Newton weight, So take note, Newton is a unit of weight, A 100 Newton weight rests on a 30-degree inclined plane. So neglecting friction, so how much pull must one exert to bring the weight up the plane? Okay. So in this problem, so it's almost similar, to example number 1, but then anyway, we are asked, to calculate the force needed, so to exert and force needed to be exerted, so to bring, so to bring the weight, so up the plane. Okay. So when you say force exerted, so the effective force, so take note, the effective force that can move the body must be parallel to the plane. So if you have, for example, let us say, let us say that okay. So let us say that you have their plane, and then you have their, shall I say, a box, and then you exert their force F. So take note that the force F, so this is not the effective force, So this is not the effective force that can move, So the weight, or this block up the plane. So assuming that the force exerted is 200 Newton, for example, so it doesn't mean that the 200 Newton force is the effective force that pull the block, So up the inclined plane. So the effective force actually is the component of the force that is parallel to the plane. No? So this force, shall we say P. So it's only the force P that is actually the effective force that pushes the block, no? Or that brings the block up the plane. So it's not the 200 Newton force. So in this problem, we are asked, no? So what would be, no? What would be the force that must be, or how much pull must one exert to bring the weight, okay, up the plane? So the word pull in the problem is actually the horizontal force which is parallel to the plane. Okay. So take note, we have 100 Newton and then it rests on a 30-degree inclined plane. So neglecting friction. So how much would be the pull needed? Okay. So, okay. So, okay. So in the second problem, so this would be for problem number 2, no? So you have there the reference horizontal axis, no? So this would be set as our reference. So this, we have there the plane, so which is 30 degrees na inclined with reference to the horizontal axis, and then you have there the box. Okay, so now please do take note, no, that regardless of uh, how we position the box, no, or the object, no, whether it is placed, no, horizontally or in an inclined plane, the weight, no, so take note, the weight of the object is always positioned vertically. So meaning to say that the weight, no, of the object will always be positioned vertically downward. So this would be 100 Newton. So regardless how we position the box, no, so how much is the inclined angle, so take note, the weight will always be positioned vertically. Okay? And then, according to the problem, we are being asked how much pull is needed, no? So, or how much force is needed to push or to pull the box. So, since this is the inclined plane, no? So, the inclined plane, so we need a force, or we need the effective, no? So, force which is parallel, not to the inclined plane. So, we have this force, shall we say, P. Okay, force P. Okay, so how much would be force P, no? So in order to pull the box, no, upward, okay? So in this analysis, no, so what we're going to do is reset, no? So for example, uh, this is the inclined plane, okay? And then this would be the force, 100 Newton, the weight of the object, so that's 100 Newton. Okay, so for simplicity, we can set this one, no? So we can set this one as our imaginary x-axis. And then, of course, this one also is set as our imaginary y-axis. Okay, such that the force P, okay, take note, the force P, this one, is the component of the 100 Newton force along the imaginary x-axis. No? So this would be the force P. Okay? And if you try to take a look at this one, the 100 Newton, okay, is acting at an angle of, so take note, no? So take note, the reference, no? So let us say this is the reference line. So if this is 30 degrees, no? So this is the reference line. So if this is 30, and we know the fact, no? So that right angle is 90 degrees, no? So meaning to say, this angle here is 60 degrees, okay? So 30 and 60, no? So that's 90 degrees, no? So therefore, we can calculate, no, from our formula presented a while ago. So the component P, no? So we have here the force P. So that's equivalent to, okay, so try to take a look at this one. So that is equal to 100 cosine of 60 degrees. No? So that is 100 times cosine of 60 degrees. No? So that's actually 50 Newton. Okay, so now if you cannot imagine how we create this 100 cosine of 60, so just have this one. No? So we have there, okay. Okay. So let us say we have 100 Newton, and then this would be your force P, and then this would be the y-axis, no? So the component, no? So shall we say Fy, that would be Fy and P, 100 Newton, and then theta. So if you try to look at, P is the adjacent side, so P is 100 cosine of theta, which is 60. So we have there 50 Newton as the force needed in order to pull. No, so it's actually the force must be greater than 50 Newton. No, so in order to bring the box upward. Okay, so we can check now if we have 50 Newton from the traces. So we have the check, no? So that's in letter A, no? So that's okay. So that's 50 Newton, no? As the answer. Okay. So now we'll proceed to the next topic, which is the resultant, no? So resultant force. So basically, the definition of the resultant force is, or a resultant force is a single force, no? So which can replace a given number of forces, and then it will still have the same effect, no, as with those number of forces. So if you have three forces, no, acting in, shall we say, different direction, you can replace those three, for example, with a single force. And that single force, which can replace the three forces, is called the resultant force. Okay? Now, we will be talking about the coplanar and the concurrent forces. No? So, we define first. No? So, what are coplanar forces? And then we define first. Then, also the concurrent forces. Okay? So the first one is the coplanar forces. So these are forces that lie on the same plane. Okay? Whereas concurrent forces, so these are forces whose lines of action pass through a single point. No? So we will be discussing two. So when you say coplanar, so take note, no? So coplanar means on the same plane. Concurrent means the forces lie, no? So they have a common point. Whereas the second type of force, the non-concurrent force system. So non-concurrent forces, so these are forces that does not have a common point, no? So example of these are couple forces, no, a couple, no? So basically, when you say couple, that's two parallel forces, no? So from our geometry, we define parallel lines, no? So as two lines that will never intersect. So for non-concurrent force system, we expect forces, no? So that do not have a common point of intersection. Okay? So we will be focusing our attention first, no? So to the coplanar concurrent force system, and then later on we will be focusing we will shift to coplanar non-concurrent force system. Okay? So take note that the coverage, no, or the content of the um, lecture will be focusing only to coplanar forces. Okay, so which means that these forces are on the same plane. No, so non-coplanar forces, we do not, or we exclude that one here. Okay, so particularly, although we can analyze non-coplanar forces using the first topic discussed, no? So the components of a force, but then the topic that will be presented to you in this lecture focuses only to coplanar forces. So meaning to say we will be discussing, no, forces on the same plane. So meaning to say we have on the x and y axis, no? So, okay. So, resultant force, no? So, assuming that we have coplanar concurrent force system, so we have three forces here. So, the resultant force, no, of the three is given by this one, no? So, Fr, the resultant force which acts at an angle of theta r. Okay, so how do we calculate, no, the resultant force, no? So the resultant force can be calculated by, no, so mathematically it can be calculated by first summing up all the x component of the force, and then you sum all the x component of the force, and then have the x component of the force raised to the second power, no? And then add it with, no, so the summation of the y components, no? And of course you have to take note, no, of the sign. So for example, like this one, no? So assuming that we have, for example, x-axis and then y-axis, no? And then let us say that you have x component here, shall we say F1, and then you have there, shall we say, F2, no? So the total force, of course, F1 is, or must be denoted as positive force because it is located in the positive x-axis. Whereas F2 will be denoted as negative force because it's in the negative x-axis. Similarly, we can take a look at the y component, no? So if the force is weighted, no, or the direction of the force is upward, so you can have it positive force, and then if the direction is downward, so you can have it negative force. So you have to consider the sign, no, so of the forces or the components, no, the x and the y axis, no. So before you can add all of them, okay. Or if we can make use, no, or we can make use of the complex number solution. So basically, you just add the forces, no? So in polar form, okay, all together. Anyway, our calculators, no? So the calculators nowadays can perform complex number operation, no? So simply shift your calculators to complex number mode, and then of course add all the forces. We call this one vectorial, no, vectorial addition, because we have to consider the magnitude at the same time the direction, no, of each force. Okay, so now we have to take a look at the examples 3 and 4. Okay, for coplanar and then concurrent forces. Okay, so okay, so in this example, no, so in example number 3, so we have there a pilot, no, so example number 3, so the pilot of an airplane flying on a straight course. Okay, so knows from his instrument that his airspeed is 300 miles per hour. Now that's not 300 meters per hour. No, so mph is usually designated as miles per hour. Okay, so 300 miles per hour. So basically that is the speed of the plane. So the pilot knows that a 60 miles per hour gale is blowing. So gale is actually another term for strong wind. Okay, so 60 miles per hour strong wind is blowing at an angle of 60 degrees to his course. Okay, so determine the velocity relative to the ground. Okay, so again, take note of the data. You have there the plane, so and then you have there the strong wind blowing at 60 miles per hour. Okay, so and then we need to determine, no, so the velocity of the plane relative to the ground. Or basically, if someone is in the ground, so the relative velocity of the plane to the ground is the one that can be seen, no? So if you are, for example, you're the one on the ground, so how much or what would be the speed of the plane from your perspective? We know that the plane is traveling 300 miles per hour, right? But then there is a strong wind, no, so blowing. Blowing at an angle of 60 degrees to his course, meaning to say that the wind is pushing the plane, no, so, from the statement to his course. So it's actually blowing, no, in the same direction as with the plane. Okay, so we are asked to determine, no, so the velocity of the plane relative to the ground. Okay, so let us solve, no. Okay, so this would be, for example, number 3. Okay, so assuming that this is the reference line, so we have the reference line, so the plane, as we can see, no, so that's according to the problem, that's flying at 300 miles per hour. Okay, and then so this would be the ground. Okay, so shall we say this would be the ground? Okay, and then another, or according to the problem, a wind, no, is blowing to the course of the plane at an angle of 60. So it's not stated whether it's upward or downward, but you can have it downward or upward. The answer will not be affected. So this would be the plane or the wind. Okay, so which blows at the magnitude of, let me verify first, no? 60 miles per hour. Okay. So which is also acting at 60 degrees. No? So if you are in the ground, okay, so basically the question is asking for, in your own perspective, what is the speed of the plane? No? So, okay, so for concurrent forces, no? Concurrent forces, we simply calculate, no? So, coplanar concurrent, no? So, first is we need to calculate, no? The components of the force, no? For example, if we try to take a look at the wind, considering the wind, so this would be the direction or the x component, no? So we will devote this one as our imaginary x-axis, and then, of course, this one. So this would be the y-axis, okay? So the plane or the wind, no? So which has the x and y component, no? So wind x component, wind y component, okay? So we can calculate, no? So the summation of the forces along x component would be, so for the airplane, that's 300, okay? So plus 60 cosine of 60 degrees, right? Okay, so this is the x component. Summation of the forces along y-axis, that would be 60 sine of 60 degrees. No? So this would be the y component of the wing. Okay. So for the airplane, so the component along the y-axis is 0, no? Because it's actually running horizontally. No? So therefore, the component along the y is 0, no? So such that if we try to use, no? So the formula, the resultant speed, no? So shall we say FR, no? So we just denote it FR. So that is equivalent to summation of Fx square plus summation of Fy square. Okay? So then we can calculate it as, let me check. No? So can we have your calculators? Okay, so and then plus, okay, 60 sine of 60, and then we took the square root of it, so the answer is 334 miles per hour. Okay, or if we can use the notation, no, or what we call the um, complex number solution, so that is, we just simply have FR, so that would be 60 acting at 60 degrees plus 300. No? So no need to write angle 0, or you have it angle 0. So FR would be still, okay, let us check, no? Again, shift your calculator to okay, shift your calculators to complex mode. Okay. And then you will have, no? So still you will have mode, okay. So still you will have the magnitude of FR to be 334 miles per hour. Okay, so try to take a look. So we have the same. Okay, but then the of course, no, the length, no, of the solution. So we can have the complex mode of calculation as the shortest available. No? Well, depending on the situation, so you still have to learn, no, how to calculate using this way. Okay, so Okay. And then we'll proceed no, to the next. Before that, we'll try to check no, so 334 MPH. We'll try to check if it's available. Okay, so yes, it's letter A, 334 MPH, no? Okay. And then we go to the fourth example. Okay, for the fourth example, so we have here two forces, so F1 and F2 acting, no? So upon a body in such a manner that the resultant force has a magnitude equal to that of F1, okay? And makes an angle 90 degrees with F1. So let F1 be 10 pounds. So find the magnitude of F2, okay? So this is somehow a tricky question, no? So to try to take a look at example number 4, no? So that's we have two forces F1 and F2, no? So F1 is given to be 90 degrees, no? I'm sorry, F1 is 10 pounds, no? So 10 pounds, the direction of which is not given. Okay, so but the resultant force, no? So the resultant force, FR, is given to be, no? As mentioned, that's the same as with F1. So meaning to say the resultant force is still 10 pounds. However, the direction of F1 no, is said to be 90 degrees with respect to FR, no, or the resultant force, no. The resultant force R, so the magnitude of which is equal to F1, and it makes an angle of 90 degrees with F1. We are asked to calculate, no. We are asked to calculate the magnitude of F2. Okay. So best way is to, of course, no, draw the free body diagram. Let us proceed. No? Okay, so okay. So if we let no, or if we have the imaginary x and y axis, no? So let us say this would be the x axis and then this would be the y axis. Okay. So now, according to the problem, F1 and the resultant force are both 10 pounds. So for simplicity, okay, for simplicity, we can say, no, we can say that F1, okay, so we need to have one of the force given in the problem to be our reference, no? So we can have F1, okay, for example, we need, or we have F1 here. So the resultant force, according to the problem, is 90 degrees, no, away from F1. That is why we need to have the reference, because we need to plot, no, so the resultant force, which is 90 degrees, no, from F1. So the 90 degrees no, from F1, if you try to take a look, you might consider having resultant force here or the resultant force downward, no. So regardless of which one you choose, then it will not affect, no, so the answer to the problem. So shall we say, no, shall we say that the resultant force is 90 degrees, no, and then we choose it to be, or to have a direction upward, no? So this would be R. So meaning to say F1 and R are both 10 pounds, no? And then F2 is unknown, no? So we do not know. We do not know what's the direction and magnitude of F2, right? So basically we have these two forces, no? So we can make use of complex notation, no? So we know that the resultant force, so the resultant force R, so that is equivalent to the summation of F1 plus F2, right? Okay, so we didn't say, no? So take note, this is vectorial, no? So vectorial addition, no? So because we cannot add directly two forces which are, or two forces, no? Which are located, no? In different directions, no? So we just have to, or we can add them directly, but we add them vectorially, okay? Vector. Okay, so meaning to say we have to consider the direction also, okay? R then is basically R, no? So that's 10 pounds from the illustration that is acting 90 degrees. So that is equal to, no? So that is equal to F1. So 10 pounds, 0 degrees, and then plus F2. So F2 cannot be, we do not draw, no? So we do not plot the position of F2 because it's unknown. Okay? So F2 then can be calculated as, no? So that's 10 angle 90 minus 10 angle 0. So that would be, so if you try to calculate that, so you have there an angle of, or the answer would be 14.14 angle 135 degrees. Basically, 90, 180. So F2 is actually here, no? Somehow here. And then the angle is 135 degrees. So that's actually the position supposedly of F2. So the resultant force is 10 acting at this angle, 90. Okay, so basically the answer to the problem is this one, 14.14. No? So if you try to take a look at, okay, okay, 14.14. No? So basically, if you try to take a look at the illustration, the resultant force, no, take note, the resultant force will always be, okay, so it will always be in between. No? So if you have there two forces, so the resultant force will always be in between the two. No? So just like with this one, no? So that F2, F1, resultant force is, of course, now in between the two forces. Okay? So we have, no? So problem number 4 is already settled, no? So we will move, no? So to the next topic, which is the coplanar non-concurrent force system. Okay, so okay. So okay. So as I've said, no, so the second part, no, in a force system, okay, so or topic resultant force, no, will be about coplanar but non-concurrent. So meaning to say the forces given in a force system does not have a common point, no. And then we define here a moment of the force, no, moment of a force. No, so moment is defined as the measure, no, of its rotational effect. Okay, so moment is defined as the magnitude of the force. The moment of, by the way, moment can be defined, no, as the magnitude of the force multiplied by the perpendicular distance to the given point. Okay. Now, if you are not familiar with the word moment, no, so it's actually different in meaning, no. So as with the ordinary word moment that we use from time to time, like this is my moment, no. So that's the moment of a force, so it's different, no? So moment of a force is similarly or can be used, no? So synonymously, no? So it's synonymous to the word torque, okay? Torque. So take note that force multiplied by distance is supposed to be a unit of energy, no? Or a formula for energy, no? Force like Newton multiplied by meter. So that's supposedly joule, right? But when we calculate moment or torque, so we do not, torque or moment is not a unit, no? So or the unit of moment or torque is not a unit of energy, okay? So why? Because the distinction between torque and energy is that torque uses the perpendicular distance, while energy, no, so when you say or when we calculate energy, that is actually the parallel distance, no, so to the given force. So for example, you have there a force F. So to calculate for the energy or the work done, so that is force multiplied by the horizontal distance, not the perpendicular distance. But if you multiply it with the perpendicular distance, then you are considering the calculation of a torque or moment. Okay, so okay, and then the resultant force, no, of the three, okay, the resultant force can be calculated, no, using the same formula. Okay, and then we can calculate for the distance d, no, so the distance d, that is the distance, no, from the reference point. Okay, so that is equal to the summation of moment, no, so multiplied or divided by the magnitude of the resultant force, no. So the same way we can calculate for the resultant force, no, so that's the summation of fx to the power of 2 plus the summation of fy, no, so to the power of 2. Okay, so and then we we use the concept, no, to solve, no, for example number 5. Okay, so and then it will be followed by a separate or another topic, no. So but before that, we'll try to focus first in example number 5, no. So okay, so in example number 5, okay, so we have 6 weights, no? So given to be 30, 20, 40, 25, 10, and 35 pounds, no? Hung in one plane, no? So from horizontal support at distances, no? 2, 3, 5, 7, 10, and 12 feet, respectively. No? So how far from the wall will a single force replace these 6 forces? Okay, so anyway, again, no, before we can before we can calculate, no, so we need to draw the free body diagram. Okay, so let me, okay, okay, so that would be, okay. So there is this horizontal plane, no, so assuming this would be for problem number 5. So assuming this is the wall, and then you have their horizontal plane, no? According to the problem, we have this number of forces, so 30, 20, 40. Okay, so we have this 1, 2, 3, 4, 5, 6 forces, no? Okay, so we have the 6 forces. So we have force 1, 6. Okay, so the magnitude of which the 30, 20, 40. Okay, 30, 20. So this would be 30, 20, 40, 25, 10, and 35. So that's 25, 10, and 35. Okay. So the distance, no, of these forces from the wall, so it's given as 2, 3, 5, 7, 10, and 12. 2, 3. So the distance would be 2, 3, 5, 7. Let me check. 2, 3, 5, 7, 10, and 12. 2 feet, 3 feet, 5 feet, 7, 10. No? So that's 3 and 12. Okay? So actually, this is 2 feet, then 3 feet, then 5, then 7, then 10, and 12. Okay? So according to the problem, we are being asked, no, to calculate the resultant force. So this would be the resultant force, no, shall we say FR. Okay, so with the distance D, no, so let us say D from the wall. Okay, so the question is, how far, no? So the problem is asking for how far, no? So is the resultant, or if we remove all the forces, no? So if we remove all the forces and replace it with a single force, and then this single force is termed as FR, how far is FR from the wall? Therefore, the reference point is the wall, no? So this one. So this will be the reference point, so D. So we begin, okay, we use, these are all coplanar forces but non-concurrent, no? So we begin with, no, the calculation of the resultant force. So the resultant force, Fr, is equal to the summation of the forces along y-axis, now since all of the forces are situated downward, no, or all of the forces now are pointing downward. So we can then say that the forces, no, so will be equal to. So we just sum it all. So 30 plus 20, that's 50, plus 40, 90. So, and then plus 10, so that's 100. So we have there 160. Okay. The unit of which is pounds. Okay. And then the moment equation. No? So we then say that the moment of the resultant force, so the moment is the resultant force multiplied by the distance to the reference point. That is equal to, no? According to the principle stated a while ago, that is equal to sum of all the moments, no? The summation of all the moments coming from the individual forces. No? So that is moment. So that is for the force 1, 30 multiplied by 2. Okay? Plus 20 multiplied by the distance is 3 plus 40 pounds multiplied by 5. Okay? plus 25 multiplied by 7, okay, plus 10 multiplied by course 10 feet. And lastly, 35 multiplied by 12. Okay? So, FR is said to be 160. We can calculate D. No? So, we can calculate D as, can we calculate 20 times 3 plus 40 times 5 plus 25 times 9 plus, sorry, 25 times 7 plus, okay, times 12 divided by 160. So the answer is 6.34 feet. Okay. So that's 6.34 feet. Let us check now if we have this value no from the choices. So we have in letter B, no, 6.34. This one. Okay. So after which we proceed, no, we proceed to the next topic. Okay. So which is about equilibrium, no? So equilibrium, no, of a coplanar concurrent force system. Okay. And then after which we then proceed to equilibrium of coplanar non-concurrent force system. Okay. And then we have 5 examples, no, for the topic. Okay. So, and then we'll proceed to another topic, no? Okay, so for statics. Okay. So to begin with, no? So to begin with, we define, no? So what is equilibrium, no? So since we are talking about statics, no? So we begin with the analysis with the body at rest, no? So equilibrium is the state of balance, no, of a rigid body. So a body is said to be in equilibrium, of course, when it is at rest. Okay. So if the object is moving, then therefore equilibrium is not achieved. Okay. So how do we analyze, no? How do we analyze problems, no, or topics about equilibrium? So we start first by studying, no? So coplanar concurrent force system. So we already know what are concurrent force system, and later on we begin with the non-concurrent force system. I mean, we followed, no, so the analysis with non-concurrent force system. Okay. So when you say concurrent again, concurrent force system, so there is a common point, no? So let us say we have this common point, okay, for 3 forces. So we can make use of, okay, by the way, when we say equilibrium, so the body is said to be at rest, therefore the resultant force is 0. So the resultant force, when the resultant force is not 0, therefore the system or the body will be somehow expected to move, no? Or basically equilibrium is not achieved, no? So take note, the resultant force is 0. Okay, the x component, the resultant force in the x component is 0. The resultant force in the y component is also 0. Okay, so for concurrent force system, so we use, no? So we can make use of this well-known theorem. So the Lamis theorem. Okay, so which is given by, no? So the equation, this one. So F1 over sine beta plus F2 over sine theta, F3 is equal to sine of alpha. Or basically, if you shall we say forgot about Lami's theorem, just remember that in equilibrium, the summation of the forces or the resultant force, no, of the system is zero. And of course, we know how to calculate the resultant force, right? So just use the concept that the resultant force is zero or the net force is zero, or we can make use. So Lami's theorem is somehow a shorthand method, no? Uh, in using, no, or in solving problems in statics under equilibrium. Okay. So anyway, let me show you some examples, no, on how we can make use of this theorem. Okay. So we have two examples, no, for this one. We have example number 6 and number 7. Okay. So okay, we try to take a look first, no, for example number 6. No? So again, since we are shifting screens from time to time, please do consider uh, gathering data, no? So such that when we solve the problem, you will have the data, no? So as presented in the example. Okay, so the example number 6, we have there a box, no? So weighing 20,000 pounds. So it's suspended by a cable 100 feet long. So what horizontal pull is necessary to hold it 5 feet from the vertical position? Okay. So again, no, for simplicity, we can draw the free body diagram. No? Okay. So okay. So let us say initially, now according to the problem, so this would be for problem number 6. So initially, we have there a box. So this would be the box. So the weight of the box, no? So the weight of the box is 20,000 pounds with a cable 1,000 feet. No? Okay. So the box is weighing 20,000 pounds. And this is 1,000 feet, no? According to the problem. So a force is used to pull the box, no, sideways. So meaning to say a force is applied. So in such a way that the system will look like this one. So you have there the cable and then the box. Okay, so then the force F is used to pull. So regardless the box is pulled or not, the weight of the box is always pointed downwards. No? That's 20,000 pounds. So the box is, or the force is used to hold the box. No? So in such a way that the, how do we call this one? The box will be maintained at a distance. No? Let me check the distance. No? So that's 5 feet. So in such a way that the distance from the center is 5 feet. So this one, so that's 1,000 feet. And then of course, do not discount the word tension. So the rope, no, so which holds the box, no, from the roof, no, so we'll also experience tension. So therefore, if we draw the free body diagram, so we have there the force F, the weight of the box, and of course the tension, no? So experienced by tension. That one, no? So okay. So how do we calculate the force P? No? I mean the force F. Okay, so let me so we can make use this one. We can denote this one alpha, so this one beta, and then shall we say gamma. Okay? So according to Lamis theorem, you can remember, so Lamis theorem is T over the sine of the opposite angle, no? Sine of, that is equal to F sine of beta, and then weight sine of gamma. So as you can see, we do not have the value for the force. We do not have also the value for the tension. So the only known data here is the weight and this angle gamma, okay, which is of course equal to 90 degrees. No? So this is where we can make use of the distances given. No? So if you try to take a look at this one, so this is 1,000, and then this is 5, and then this is theta. No? So if you try to take a look at this one, theta can be calculated as, how do we calculate theta? No? So theta is equivalent to, or cosine, no? Cosine of theta, that is 5 over 1,000. So theta then is equal to the inverse cosine, no? So that is okay. Okay, so that is 89.71. Okay, so now we have theta already. So we can calculate gamma. So gamma is equal to 180 degrees. No? So that is the straight angle, straight line angle, this one, 180. And then this would be theta. So gamma is minus 89.71. So we can have 180 minus 89.71. So giving us 90.29. Okay. So such that we can find two possible combination. No? So the unknown is F. So we need to, okay, since the unknown is F, so we need to find the angle beta, by the way. No? So the angle beta. Okay, so anyway, beta can be calculated. No? So beta can be calculated as this angle going here, that's 270 degrees minus alpha. So beta then is equal to 90.29. So this is 179.71. Okay, so you notice that the angles, no? So the distance, no, the horizontal distance is very small as compared to the total length, no, of the cable. Okay, so such that we can have the force, no, sine of 179.81. So that is equal to, so since we have the known weight, so that's 20,000 divided by sine of alpha, that's 90.91. Okay, so this is the field represented by Lamy, no? So we can calculate F then as equal to, no? So just multiply 20,000 times sine of 179.81 and divide it with sine of 90.91. Okay? So and you will have there a force of 66.33 pounds. Okay, so let me check if we have that number. Okay. Uh, let let us what horizontal force necessary to hold it 5 feet from the vertical position? Okay, let me check the process. Now perhaps we have uh, so let us check. So that's 10,000, 20,000, and then this is 5 feet. No? So theta here is, okay, so let me calculate theta first. No? Um, 5 feet from the horizontal, so cosine of theta. 1,000, let me check. No? So, okay, let me check. No? So that's 7 and 14. Okay. So, okay, and okay, let me check now. So where did we uh, gone wrong, no? With the okay, so that's Mhm. Okay, so upon recalculation, so the answer, no, so the answer given from recalculation, that's 66.33. No, so which I guess there would be some, or there is, no, there is some error with the. Let me share, no, again the problem. So the presented choices, no, so does not show 66, no, pounds. So we leave it as the answer, no, for the given number 6, no, so that's um, 66 point. Let me check again, no, so that's 66 point 33. Okay, so okay, 66.33 as our um, answer. Okay, and then we proceed. Okay, we proceed to example number 7. Okay, so in example number 7, we have, no. So this is still in relation to concurrent for system. Okay. So in example number 7, so you have the 50-pound block hangs from a cord, no? So which is knotted to two other cords na fastened to the ceiling. So making an angle of 30 degrees and 60 degrees respectively. So find the biggest tension on either cord. Okay. So in example number 7, so uh, we have a block, no, so which is hung. Okay, so to the ceiling using two cords, no, so fastened. Two cords are fastened, no, to the ceiling, so it makes an angle of 30 degrees and 60 degrees respectively. So find the biggest tension on either cord. Okay, so let's try to take a use again of Lami's theorem. So by the way, the intention of the, do not forget, by the way, that the intention of the method used, no, is the shortest possible solution. So which may, or which you can make use, no, so for board exam preparation purposes also. So as much as possible during the discussion, so we will be using the shortest possible method, no? So that can be applied to board exam setting. Okay, so let me share again. No? So let's check. Okay, now okay. So according to the problem, so initially we have the box again. So the box is being fastened, no? So from 2 points. So situated this one and this one, no? The weight of the box is given to be 50 pounds. So this would be 50 pounds. The ropes, no? So makes an angle of 30 degrees and 60 degrees, no? So it doesn't matter which one is 60 or which one is 30. No? So the question is asking for the biggest tension, no, of the rope. So since the ropes, no, experience the stretching because of the weight, so might as well we may consider that the rope 1 experiences tension T1, and of course the rope number 2 experience tension T2. Okay? So if we try to take a look, or if we try to draw the free body diagram of the forces, okay, so it will look like this one, no? So the weight, the 50-pound weight. So you have their T2, and of course you have their T1. Okay. So for T1, so you have the 30 degrees here and then 60 degrees here for T2. Okay, so of course the angle in between, this one, so the total angle is 180, no, for straight line angle, this one. So this 180. So 180 minus 90, of course, no? So the angle here is 90 degrees. Okay? Now, if we can make use of Lamy's theorem, so by the way, the angle here is 120 degrees, 90 plus 30, and the angle here is 90 plus 60, that's 150 degrees, right? Okay, so we begin with, no, so writing Lamy's theorem. So 50 pounds divided by sine of 90. So that is equal to T1 over sine of 150. That is equal to T2 divided by sine of 120. So we do not know which one experiences so the biggest tension. So we'll just try to solve individually. So first is we pair this one. So that's 50 sine of 90. That is T1 sine of 150. And then the other one, 50 over sine 90. That is T2 over sine 120. So we can make, or we can calculate T1. So just multiply 50 times sine of 150 divided by sine of 90. So the answer is 25 pounds. T2 on the other hand would be, okay, 50 times sine of 120 divided by sine of 90. So we have there 43.3 pounds. So basically from the two answers, T2 is the biggest tension experienced by the rope, no? So we can check, no? That's 43.3. Okay, so the closest, no, answer is the 43.1, no? So 43.1. So